Now that we're familiar with signal flow graphs, the next thing that we want to look at is how can we reduce that signal flow graph to just one equivalent transfer function. And so as I mentioned before, we're going to use something called Mason's rule to do that. So again, our main goal here is we want to reduce our whole signal flow graph to one single transfer function. And what we're ultimately going to see is we can do this with just a single formula using Mason's rule. So unlike with our block diagram algebra, where we sort of have to step through and recognize systems and combine and then keep sort of combining as we go, with Mason's rule, we are going to go through, identify some important sort of equations, plug it into this single equation or single formula, and that's going to give us our answer. So we're still going to have to deal with some algebra, but some might say that this process is a little more straightforward than the block diagram algebra. So in order to sort of define some of these important terms that are going to go into our formula, we need to look at a signal flow graph as an example. We don't need to, but it's going to be helpful. And so in this video, we're going to spend the rest of the time sort of describing what these relevant items are. And then in the next video, we're actually going to introduce Mason's rule. In the videos following that, we're going to get some practice with some examples. So notice in this signal flow graph, I've got my signals, which are the nodes labeled with blue letters, and our systems, which are the branches connecting the nodes, are labeled with black letters. Just like in the previous video, all of these signals and systems are functions of S. I've not written that explicitly just to save some space here and make it a little less cluttered. Okay, so let's get into talking about some of these important parameters. The first one that we want to talk about is something called our loop gain. And so as the name implies, it's just the product of branch gains around a loop. So product of our branch gains around a loop. And so let's be more explicit with how we define a loop. So it's going to be around a path that starts and ends at the same point. So starts and ends at the same point or the same node. And while doing that, it also can't pass through any node more than once. So without passing through any node more than once. So coming back to our sort of example signal flow graph here, we can look, sort of work on our way left to right. One loop is if we start here at V1, we go through G2, and then we come down through H1, and now we're back where we started. So again, the loop gain is going to be the product of the branch gains. So in this case, the product of those gains is just G2 times H1. And so sometimes we might define our loop gains as L1, so we can say L1 is equal to G2 H1. All right, we have a very similar structure over here. If we start at V3, go through V4, and then back to V3, we see that loop gain is going to be G4 times H2. So we can say loop gain 2 is G4 times H2. All right, so we're finding these loops pretty easy. Let's look at an example of what would not be a loop. So let's say we start at V3, and we notice we have these two paths, G6 and G6 and G5 in parallel. So let's say we go V3 to V4 to V5, back to V3, and then we come through here again, and we go through G6, and then back through here again. So that would not be a loop, because what we've done is we've gone through these nodes multiple times. So that's where that sort of second part of our definition of we can't go through the same node more than once comes into play. So of course we're starting and ending at the same spot. So if we do, for instance, V3 to V4 to V5, and then back like this, that would be a loop. We started and ended at V3, but we've not gone through V3 twice. So let's add that path or that loop gain. So we've got G4 times G5 times H3. Switch back to my pen. So G4 times G5 times H3. And then of course we can do a very similar path by just substituting our parallel branch. So we can do G4, G6, H3. And so we don't have any other loops, so those are our 4 loop gains for this system. So G4, G6, and H3. So the next important item that we want to talk about is our forward path gain. So forward path gain. And so similar idea to our loop gain, except now we're talking about the product of gains along a forward path. Okay, so the product of our branch gains along forward path from our overall input. So I'll put input R to our output C. And so one sort of little caveat here, and it's maybe not super clear with what I've already written, is we can only go in the forward direction here. So only going forward. So we shouldn't be going through any of those H blocks when we're defining our forward path gain. So in this system, we have 2 forward path gains. So we can go through G1, G2, G3, G4, G5, and G7. So sort of just a straight shot through. And of course, the other alternative is we just take that G6 parallel branch. So we have something that looks like that. So those are our 2 forward path gains, or those are our 2 forward paths. So let's write our forward path gains. So the first one we said was G1, G2, G3, G4, G5, and G7. And then for our second one, we're just going to do the same thing, except we replace our G5. And it looks like I got an extra G there. So we're just going to replace our G5 with G6. All right, so those are our 2 forward path gains. So one other item that we need to define, and then one other sort of adjustment on that item in order to be ready for our Mason's rule equation. So the next item to define is our non-touching loops. And so again, the name is pretty self-explanatory here. These are just loops that don't touch, or more sort of explicitly, we can say loops that don't have any node in common. So loops that do not have any node in common. And so coming back up to our signal flow graph, we can see, for instance, this loop over here, which we called L1, is sort of all by itself. And so it's not touching any of our other 3 loops. So we said we had one loop here. Let's change colors. We also had a loop here. And then we also had a loop here. And so what we can see with those 3 loops on the right is that all of them share, they all touch at nodes V3, V4, and then our 2 of those 3 touch at V5 as well. So in this case, our non-touching loops are going to be limited to our loop 1 on the left, and that's non-touching with our other 3 loops. So let's go ahead and clear that. Okay, so in this case, we can say our loop gain, which was G2H1, our loop gain L1, does not share nodes with our other 3 loop gain. And so our other loops, we had G4, H2, G4, G5, H3, and G4, G6, H3. Okay, so now sort of building on this idea of non-touching loops, in our equation we're going to have a term that's related to non-touching loop gains. So non-touching loop gain. And so what this is sort of the product of our loop gains taken at 2 at a time, 3 at a time, 4 at a time, and we'll describe this a little more clearly as we're looking at some examples later on. So product of our loop gains, and of course these are our non-touching loop gains. So I'm going to just say NT, non-touching loop gains. Taken 2, 3, 4, etc., at a time. In this system, we're going to see we can only do 2 at a time, but for more complicated systems, we'll have to worry about that. Basically, what this is saying, sort of more simplistically, is we're going through the non-touching loops while moving left to right. So in this system, we can only do 2 at a time. So for this system, can only do non-touching loop gains taken 2 at a time. And the reason for that, again, sort of simplistically, we can think of it as going through multiple loops as we move from left to right. So coming back up to our system, let's say we're sort of moving from R to C, so we can go through this loop, and then we can go through this loop. Both of those are non-touching loops. So remember, this is a non-touching loop gain, so that would be sort of one combination. Second combination would be our first loop. We could do our third loop there, like that. We could also have, we go through this loop, so we go through this loop, and then we go up through our G6. And so again, we're not actually following along this path, but we're just saying, sort of, this is a different way to visualize our non-touching loop gains. And again, when we work some examples, I think this is going to be a little more clear. So basically, as we said, our non-touching loops, this L1 doesn't touch the other 3, so taking 2 at a time, we're going to have the product of this and this, of our L1 and our L3, and our L1 and our L4. So what that looks like then is our non-touching loop gains taken 2 at a time. We're going to have G2H1 times G4H2. So again, remember, this is the product. So for our next one, we have G2H1 times G4, G5, and H3. And then for the last one, it's just the same, except we are replacing our G5 with G6. So now we're going to get rid of that, and we're saying this is G6. In the next video, we're going to define our Mason's rule equation, and then I think things will still be a little unclear maybe, so we'll work several examples to kind of get some practice with that.